I'd like to spend some time right here just making sure that we really understand when we can and when we cannot multiply two matrices together, because you need certain conditions to hold. So as I was alluding to earlier, you really need the number of columns in the first matrix to be equal to the number of rows in the second matrix. So we have a question at the top right here that is questioning whether product PQ or QP exists. So if we were to consider this first example right here, PQ, then really you'd be trying to take that matrix that's got those elements organized like that and multiply it with the Q matrix with the elements that are organized like that. And so the only way that you are able to actually get an answer or actually able to multiply matrices is by having those dimensions kind of line up where the columns of the first matrix is equal to the number of rows in the second matrix. So if we take a look at the dimensions of the first matrix, it's got 4 rows and 3 columns. And the second matrix has 2 rows and 4 columns. So the number of columns in the first matrix is not equal to the number of rows in the second matrix. And so we're not actually going to be able to multiply these matrices together. And you'll be able to see that because based on the prior example that we worked through, I told you that we always take a row of the first matrix and multiply it with a column of the second matrix. So if we were to pairwise multiply numbers up, you'll see that we kind of end up with some numbers or a number that doesn't have anything left to pair with, and so that's why it's not going to work out for us to be able to multiply this together. So if we cannot actually perform this operation, then that would be undefined in terms of an operation right there. So that means that PQ, it does not exist because it's an undefined operation there. If we were to try doing QP, then you would have to consider your Q matrix to be the first matrix. You'd have your 2 by 4 matrix first, and then you would have your 4 by 3 matrix second. So the dimension just kind of flip-flops. So you would have your 2 by 4 first, and then your 4 by 3 second. And so if you check the dimensions where the number of columns in the first matrix and the number of rows in the second matrix, they are the same in this particular case. So then we are actually able to always perform the operation when those two middle numbers line up. And so when you actually get your answer to this, you're going to get a matrix that has the dimensions of the outer numbers. So since those outer numbers there are 2 and 3, you're going to get an answer where the matrix is going to be a 2 by 3 matrix. So it's going to have 2 rows and 3 columns. So you're going to get numbers in those particular positions. So when you do all your pairwise multiplying and such, like when you multiply the first row with the first column, you pairwise and then add up, you're going to get that number and just kind of keep cycling through all of that to get your answer there. So down here is just kind of some examples with different matrices X, Y, and Z for you to kind of consider and think about whether or not each product would exist or not.